Calculus required continuity, and continuity was supposed to require the infinitely small, but nobody could discover what the infinitely small might be. This is the great Bertrand Russell. By now we know that infinitely small is limit. In fact, all of calculus is powered and denominated in limit. Differentiation, for example, is the limit of the rate of change, or the slope of a function at a point. It is not just the rate of change, it is the limiting value of the rate of change of a function at a point. It is the value that is consistent at the point and points arbitrarily close to it. Limit is the key here, because limit is the science of working with near zero, but not zero, infinitesimal quantities. Let us consolidate the concept and the reasons for the extensive application of limit. We have duly introduced and presented limit in the earlier lessons on motion, and the three challenges in finding the instantaneous rate of change. This lesson must be experienced only after those two lessons are well appreciated. Of course, we start with a brief revisit of what we know about limit. Also because, in this lesson, we will present a somewhat new take on limit. There is no joy, thus no learning, no thinking, unless we use every opportunity for newer narratives. Of course, it goes without saying that making of this lesson gave me immense joy, as I came to understand limit in newer ways. I am a student of mathematics, much more than being a mathematics educator. Above all, limit is almost a pure mathematical creation, a fundamental mathematical idea rather than any physical or tangible expression. And this understanding must be fully internalized to comprehensively know limit. Limit is a conceptual breakthrough, but not to be wrong, it has the most extensive applications in investigating and modeling real world. It must be well appreciated that understanding limit in a vivid physical way is challenging. Analogies and visualizations are used to get it, intuitively, but the abstractness remains. I would not get into that and undermine the mathematical essence of limit. It must first be understood conceptually, that is, analytically or mathematically. To be true, limit was developed within calculus to rigorously establish the notions of continuity, derivatives, and integrals. Recall, all of calculus is about knowing all about continuous change, and through the rate of change of all kinds. The notion of continuity is very critical in calculus. Assuredness of the continuity of the functions that we use as the proxy of the actual real situations is very important. For real situations change in a continuous manner, whatever the pace and form. So the functions that represent them must also be continuous. Without limits, there is no precision in the idea of continuity, derivative or instantaneous rates, and area and spaces of curved surfaces. And, we know, lack of precision is not mathematical. It won't be technically wrong that the edifice of calculus is built upon limit. The infinitesimal nature of finding the limit of a function at a point brings precision. Limit may also be seen as the bridge between discrete and continuous mathematics, making feasible study of continuous change. Pertinently, the way limit revolutionized mathematics, especially the mathematics to describe the behavior of continuously changing things or situations, was to accept the reality. Limit, in a way, acknowledges the physical impossibility of precise physical measurements of any kind of instantaneous values of changing quantities. Even the measurement of primary quantities will be imprecise for an instant. For example, measuring distance traveled at any instant in a motion will never be precise. The precision of the measuring instruments, and in some cases the extent of possible measurement granularity of the quantity being measured, imply inherent imprecision. Can we imagine the challenge in the measurement of rate quantities? The limitations of measurement only multiply when we talk of rate, which involves too precise measurement of two quantities in an instant. For example, for measuring speed at any instant, we need accurate measure of time and the accurate measure of distance in that time. A double whammy, indeed, measurement of rate quantities at any instant cannot be physical. The idea of limit totally took instant rate computations on a non-physical highway and made such measurements possible. Limit helped us mathematize continuous change, enabled us to mathematically mimic real-world scenarios. And how limit achieved this precise virtualization or abstraction of the real. Limit wrote on functions to precisely virtualize or abstract the real. Limit works on functions, that is, limit helps us get the rate of change of something from its function equivalent, the mathematical expression that closely matches the behavior of that thing. Functions are the most common and fundamental means of the application of limits. Limit is operable through functions. We have explored function in 2 earlier lessons, including how functions quite represent real situations. To be right, it may be added that the idea of limit is used in other mathematical contexts too, such as series and sequences. In a way, it is function that actually mathematizes real world. And limit is a nearly mathematical concept because it comes alive only on functions. This is the story of the raison d'être of limit, how it is critical for derived quantities, mathematical quantities, that cannot be physically measured, such as speed, acceleration, electric current, pressure, etc. We can now recall some key properties of limit, based on the 2 previous lessons. The idea of limit introduced a way of working with such infinitesimal quantities in which the behavior of a function is consistent. This consistency is important for finding the precise rate of change. It is to ensure that there is just one rate of change in that infinitesimal quantity of the independent variable, such as time or any other around that point. Limit helps us know if ever smaller quantities around a point do elicit more evidences of the value of the function consistently moving towards a specific or well-defined value, and this trend is true for both sides around the point. And the concept and definition of limit is fairly rigorous, ensuring mathematical precision in finding rate of change. Limit of a function is at a point, defined for a point. Limit of a function is the value of the function at that point if the function is defined and continuous at that point. By defined, we mean it is not undefined. It is discussed next in relevant detail. Additionally, however, if the function is undefined or is discontinuous at a point, the limit may still exist, but may not be equal to the value of function at the point. In a way, to be simple, limit of a function approaching a point is the value of the function at those points in the approach, arbitrarily close to the value of the function at the point being approached, but not same as the value of the function at the point. The term undefined is for operations or expressions that do not have a meaningful interpretation or result in mathematics. The common undefined quantities are listed here, and functions that have expressions of this kind at a point or interval would be considered undefined at that point or interval. Division by zero. Square root of a negative number. 0 raised to the power of 0. Logarithm of a non-positive number. Piecewise defined functions. Indeterminate forms, such as 0 by 0 or infinity by infinity domain. Restrictions wherein certain functions or operations may have restrictions that exclude certain inputs, and those inputs must not be used. If it is not obvious yet, it may be mentioned that all rate measures using limit also are the average rate of change of the function over smaller and smaller intervals around that point. Recall, operations on functions result in a function. Thus, the slope of functions is also a function, the slope function. Spectacularly, the slope function was valid for all the points on the function. Of course, the value of the slope function may vary from point to point on it to reflect the changing slope of the function. And perhaps the most interesting bit about calculus and derivatives of curves, real-world functions, is the fact of one slope function for the entire domain of the function. The derivative of a function at a point is the derivative function at all points. Think more about this to realize the beauty and simplicity that derivatives are and calculus is. The expression in the picture shows how limit of the rate formula is critical to get the instantaneous rate of change. Without the use of limit in the rate formula, we would not be able to get to the change in the value of the function in an instant, in an infinitesimal quantity of something. Limit is an idea, an operation, and a concept in mathematics that is to see if its behavior of an entity at a point is similar on points arbitrarily close to it on both sides, higher and lower. That behavior could be that of the rate of change of the function too. When we apply the idea of limit to a rate at a point, we get the same assurance that the rate at any instant arbitrarily close to the instant is same as the one at that instant. Thus, the computed rate at the point is the singular one within infinitesimal range of the point. It is the instantaneous rate. Thus, the instantaneous rate of change can only be obtained by taking limit of the rate of change at that instant. Integration strings together infinite infinitesimal quantity to compute area or volume shown in the first picture. The expression shows an integration expression. It shows the integration or stringing of the function value multiplied by the infinitesimal independent value, that is dx. The integration gives the sum of the slices of area under the curve. The use of limit in the expression is the focus of explanation in this lesson. Fx into dx represents the infinitesimal area slice under the curve at each point x, as dx changes from a to b. The value of the integration of fx into dx is the limit of the sum of the areas of the slices. It is the limiting value because as the number of slices increase and tend towards infinity, dx of each slice tends towards 0. Limit is required in getting the sum because we cannot actually sum an infinite number of infinitesimal elements fx into dx because the number of slices to be added would be infinite. Similarly, dx cannot be exactly 0 because then we would not have any slice area to sum. Thus, we have to work with near 0 and near infinity values and use the idea of limit to find the area with near 0 and near infinity values. By the way, we increase the number of slices to increase the accuracy of the integration value. The lesson on integration is the place to put this observation in perspective. More on integration is in the lesson on integration. Hope the basic idea of limit being as important in integration as in differentiation is brought home. The dedicated lesson on differential equation is ahead. Thus, this talk on limit in the context of differential equations may be a bit hard to get, but I hope to offer a simple narrative. We may start with an example of a differential equation and its solution. To the point, a differential equation is an equation that has at least one derivative term, just like it has the variables x, y, z, and it is solved to get the equation that is the integral of it. Recall, integration is antiderivative. Naturally, we integrate differential equations to get rid of the derivatives. Obviously, wherever there is integration and derivatives, there is limit. Yet it may be added that the presence of derivatives implies limit is essential for the formulation and understanding of differential equations. Similarly, the presence of integration in solution demands limit to ensure the accuracy and validity of the solution steps. Computation of limit of a function at a point is massively simplified by the concept of continuity. Continuity and graph show us the points and intervals of discontinuities, and except for those points and intervals, we do not need to compute the left-hand limit and the right-hand limit to find the limit of the function at that point. Most importantly, for a continuous function, the value of the function at a point is also the limit of the function at that point. There is little more to limit with respect to calculus and its use in continuity, differentiation, integration, and differential equations. The idea of limit as totally mathematical, anti-physical, remains highly inventive. In calculus, using functions to be purely mathematical is one of the biggest mathematical masterstroke, and hopefully the idea of limit resonates and it is well understood. Thank you. With us, you will master all the mathematics you need. Be good to you, not just others.